Hello, I'm Siang-Yun from EPFL, Switzerland. In this video, I will discuss the optimality of the buffer and splitter insertion problem in AQFP circuits. This is the outline of my presentation. After giving some background and introducing the problem, I will present three main contributions of this work. I will also give a motivative example to show the most important claim in this paper, that is, the buffer and splitter insertion problem is a scheduling problem. Finally, some experimental results will be summarized. AQFP stands for Adiabatic Quantum Flux Parametron. It is an emerging superconducting electronic technology featuring a very low energy consumption. In AQFP circuits, every gate is clocked, which causes an additional design constraint, path balancing. All paths in the logic circuits have to be of the same length, so shorter paths need to be balanced by inserting buffers. Moreover, there is the fan-out branching constraint, saying that any gate with more than one fan-out needs to be amplified by splitters. Buffers and splitters are basically the same cell in AQFP, so it makes sense to consider the two constraints together, and I will mostly just call them buffers. These two constraints do not exist in CMOS technologies, so EDA tools must be adapted to satisfy them. In previous works, buffers usually make up for more than half of the circuit area, so it is interesting to insert them in a smarter way to reduce their cost. As the technology is still rapidly developing, some assumptions must be made. The splitting capacity, SB, is how many signals a buffer cell can split into. Depending on the design of the registers, the primary inputs and outputs of the combinational circuits may or may not need to be balanced and/or branched. Our implementation is parameterized and can easily adapt to any possible assumption, and we will also study their impact in the experimental results. The buffer insertion problem is defined as follows. Given the logic circuit on the left, where the circles are logic gates, we can see that there is a gate with multiple fan-out, and there are some paths of different lengths. Without considering logic restructuring, which means without changing the interconnection between logic gates, we would like to insert buffers to legalize the circuit, fulfilling both the path balancing and the fan-out branching constraints. In the remaining of this presentation, logic gates will always be drawn as black circles and buffers will always be blue squares. A naive way of inserting buffers is shown in this animation. We fulfill the fan-out branching constraint first, because buffers also take a unit delay and will affect the path length. Then we insert as many buffers as needed on all shorter paths. Finally, a simple local optimization called retiming can be done to eliminate some buffers. This algorithm fulfills the two constraints in a straightforward way, but provides no guarantee on the optimality in terms of the number of buffers. Our first contribution is a linear time, locally optimal buffer insertion algorithm. Given the level assignment to all gates, for each gate G, we want to insert the least possible number of buffers at its fan-out to legalize the circuit. The relative levels with respect to the level of G are labeled on the left of this figure, and we assume the splitting capacity SB is 2. We insert buffers from the highest level by dividing how many edges are in the higher level by the splitting capacity and taking the ceiling. Buffers in the higher level need to be inserted first because they will contribute to the demand of more edges in the lower levels, together with the lower fan-out gates. This algorithm is optimal subject to the given level assignment, also called the schedule. In the end, it also verifies if the given schedule is legal, that is, if it is possible to insert buffers to legalize the circuit without changing the given schedule. So, given a schedule, we can insert buffers locally optimally. But globally, how do we obtain a schedule in the first place? Well, obtaining an initial schedule is not difficult. For example, we can use the well-known as soon as possible scheduling ASAP or as late as possible scheduling ALAP to obtain a schedule in linear time. In this example, we can see that although ASAP and ALAP have different configurations, they both need 6 buffers. However, if we take one part of the circuit from ALAP and the other part from ASAP, we obtain a better schedule that only needs 5 buffers. This shows that ASAP and ALAP can serve as a starting point, but they may not be the best. The problem has now become a scheduling problem. Our second contribution is an SMT formulation to solve for the globally optimal schedule. Using the algorithm of local optimal insertion on the left, we will transform the pseudocode into SMT constraints. First, as we are solving for a schedule, the primary variables will be the level assignment of each gate. For the maximum level, we use ASAP and ALAP to find a constant bound. And the for loop is unrolled using different auxiliary variables in each iteration. Also, the translated constraints are applied for each gate G in the circuit to count the buffers at their fan-out. The number of edges needed at a certain level is counted with the help of the if-then-else ITE operator. The division by SB and taking the ceiling are translated into linear inequalities. All variables are integers and SB is a constant. We also need to assert the legality of the schedule. Finally, the count variable in the pseudocode is simply a summation over all of the B variables in SMT. And we want to minimize this variable. We use the SMT optimization solver in Z3 to solve the instance. The SMT formulation can find the global optimum, but of course, it's slow and it doesn't scale. So our third contribution is a heuristic to globally optimize the schedule by moving chunks. Intuitively, a chunk is a tightly connected set of gates in a scheduled circuit that must be moved all together. Gates in a chunk are either connected at consecutive levels or separated by one level with a buffer, but that buffer is definitely needed because the lower gate has multiple fan-outs, like in chunk 3. The set of chunks form a partitioning of all the gates in the circuit, and the interfaces between chunks are where flexibilities exist to move the chunks up or down. In this example, if we try to move chunk 1 up, we eliminate one buffer on top, but we'll need 2 more buffers at the bottom. This is not good. However, if we move chunk 3 up, we eliminate 3 buffers on top and add 2 buffers at the bottom. In total, we get rid of 1 buffer, so it's a beneficial movement. For the experiment, we first compare to the state-of-the-art using the same benchmarks as them. Our SMT formulation found the global optimum on some smaller benchmarks. Some of them are small enough that both previous work and our heuristic find the optimum as well. But for some medium-sized ones, the previous work did not actually achieve the optimum, and our heuristic got very close to the optimum. Overall, we improve about 4% over state-of-the-art, and more importantly, we provide over 100 times speed up. We did the second experiment on 10 to 100 times larger benchmarks to show the scalability of our approach. With the largest benchmark, Even though applying chunked movement would take too much time, we can still provide an irredundant insertion result using ASAP ALAP and the linear time local insertion algorithm. If resource allows, chunked movement can be applied one or more iterations to further improve the result. This suggests that our approach can be seen as an anytime algorithm. Finally, we investigated the impacts of the technology assumptions, which may motivate and guide future research on the technology side. For example, we found that branching PIs will increase the number of buffers by 50%, suggesting that having high driving capacity registers at the inputs of the circuit will be beneficial. Also, when the splitting capacity of buffers decreases from 4 to 3, the number of buffers increases by 5%, but 1 to 3 splitters are better in placement. So researchers and engineers may use this data to decide on the trade-off in circuit design. To summarize, in this presentation, we learned that AQFP circuits impose two special constraints, path balancing and fan-out branching, and we need to insert buffers to satisfy them. We propose three contributions in this work. First, we have a linear time algorithm to insert buffers that is locally optimal subject to a given schedule. We have learned why the buffer insertion problem is a scheduling problem with a motivating example. To find a good schedule, our second contribution formulates the search for global optimum as an SMT problem. And our third contribution is a heuristic global optimization based on chunked movement. We have also seen that technology assumptions have great impacts on this problem. Last but not least, the implementation is open-sourced in our logic synthesis library MockTurtle. Thank you for your attention.